Hello, in this lecture we will find out the length of chord CB. In the drawing we have a semicircle. We know that the center of this semicircle is at this point, point O, and inside the semicircle we have square DEFO. This is a square. And we also know that the area of this square DEFO is equal to 5 square units. And our mission is to find out the length of this chord CB. Okay? So first of all, because of the fact that DEFO is a square, we know that all the angles inside the square are right angles. Therefore, those four angles that are inside the square are all right angles. So I write it down. This angle equals to 90 degrees. This angle it is also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle it is also equals to 90 degrees. Okay. In addition, we also know that the area of this square DEFO is equal to 5 square units. So actually, if we have here square this is a square ABCD that could be any square, and we know we will define the length of one side as x, BD equals to x units in its length. Therefore, all the other sides are also equal to x because of the fact that all the sides of any square are equal to each other. So the area of this square ABCD will be equal to x times x. X times x times x is x squared. So the area of square ABCD, that could be any square, is equal to x squared. In the next step I will copy our original square to this page and we will find out the length of one side of this square. Square DEFO. Okay. So this is square DEFO. That I copied from the original drawing. We will define the length of one side of this square as x. Therefore, all the other sides, their length will be also x. And according to the formula for any square, the area of square DEFO, here the squared brackets is the same for the area. This means the area of square DEFO. According to the new formula, it is equal to x squared from one side, but from the other side, it is given us in the question that the area of this square DEFO, it is equal to 5 square units. So from those two equations we will derive that x squared equals to 5. Here we'll take a root out of this equation and we'll get that x equals to the square root of 5 units. Okay, so we actually found out that all the sides of square DEFO are equal to the square root of 5 units. So I write it down. In the next step, we'll join points D and O together by a straight line. By joining points D and O, we actually created the right triangle DFO. Here, the right green triangle DFO is a right triangle because angle DFO is equal to 90 degrees. It is 1 out of 4 angles of the square. It is a right angle. So I will copy triangle DFO in a new page and we will implement the Pythagoras theorem in this green right triangle DFO in order to find out the length of the hypotenuse DO. Okay, so actually you I will copy the right green triangle DFO to the new page. This is the right green triangle DFO that I copied from the original drawing. We have already found out that DF equals to FO. They are all, both sides are equal to the square root of 5 units. They are the sides of the square, DEFO. Again, this angle equals to 90 degrees because it is 1 out of 4 angles of the square. And all the angles of any square are right angles. Now the only thing that is left to find is to find out the length of the hypotenuse DO. So we'll use the Pythagoras theorem in order to find out the length of the hypotenuse DO. So here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle DFO is DO, therefore the square of the hypotenuse will be equal to DO square, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to DF square plus FO square. Okay, so DO squared, that is the square of the hypotenuse, must be equal to DF square. DF equals to the square root of 5, therefore DF square will be equal to the square root of 5 squared plus FO square. FO is also equal to the square root of 5, therefore FO square will be equal to the square root of 5 squared. In conclusion, we found out that DO square, the square of the hypotenuse, equals to square root of 5 square is 5. Plus square root of 5 square is 5. So we found out that DO square equals to 5 plus 5, that is 10. We will take a root out of this equation, DO square equals to 10, and we get that DO equals to the square root of 10 units. That is to say, we found out that the hypotenuse DO equals to the square root of 10 units. You can write in the original drawing that DO equals to the square root of 10 units. Okay, what is actually DO? From one side, DO is the hypotenuse of the green right triangle DFO. But from the other side, DO is also the radius of the semicircle. Why? Because of the fact that line segment DO starts from point O, that is the center of the semicircle, and ends at point D, that is a point on the semicircle itself. This is exactly the definition of a radius. So you can write down that DO is the radius of the circle, of the semicircle, and it is equal to the square root of 10 units. That is to say, the radius of this semicircle equals to the square root of 10 units. Likewise, we'll focus on line segment OB. Line segment OB starts from point O, that is the center of the semicircle, and ends at point B, that is the point on the semicircle itself. This is exactly the definition of a radius. That is to say, OB is the radius of the semicircle, that is equal to the square root of 10 units. Likewise, in line segment AO starts from point O, that is the center of the semicircle, and ends at point A, that is a point on the semicircle itself. Therefore, AO is also the radius of the semicircle, that is equal to the square root of 10 units. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. Okay, this will be rule number 1. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So what is the meaning of this rule? The meaning of this rule is that if we have straight line AB, here AB is a straight line, and the straight line AB has two sides. It has the upper side, this is the upper side, and it has also the lower side. This is the lower side. And the rule says that the sum of the angles at one side, either in the upper side or in the lower side, the sum of the angles must be equal to 180 degrees according to this rule, rule number 1. So if we focus on the upper side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees according to this rule, rule number 1. Which angles we have at the upper side of AB at point K? We have this angle, that is angle AKL, plus this angle, that is angle BKL. In total, the sum of those two angles must be equal to 180 degrees. That is to say, angle AKL plus angle BKL must be equal to 180 degrees according to this rule, rule number 1. And the same thing is true in relation to the lower side. The sum of the angles in the lower side here at the straight line AB at point K must be equal to 180 degrees. That is to say, this angle is equal to 180 degrees. And it is very easy to see that is equal to 180 degrees. Why? Because angle AKB is a right angle, is an angle that is equal to 180 degrees. Because the definition of angle that is equal to 90 degrees is any angle that is equal to 180 degrees, it creates a straight line. And AB or AKB, it is a straight line, of course. Therefore, angle AKB, this angle equals to 180 degrees. According to this rule, rule number 1. So we can implement rule number 1 in our drawing. Why? Because in our drawing, we know that this is a semicircle. In any semicircle, always this part is the diameter of the semicircle. That is to say, AB is the diameter of the semicircle. So, if AB is the diameter of the semicircle, it is absolutely a straight line. Why? Because any diameter must be a straight line. So, I'll write it down. So, we know that AB is a straight line because it is the diameter of the semicircle. So if we focus on the upper side of the straight line AB at point O, so AB is a straight line, so at the upper side of the straight line AB at point K, at point O, again at the upper side of the straight line AB at point O, according to this rule number 1, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle, that is one out of 4 angles of the square, that is a right angle. So that is to say we have angle that is equal to 90 degrees. Plus, we have this angle, this is actually angle EOB. It is unknown angle. It is the missing angle. Plus angle EOB. This angle. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. Again, 90 degrees plus angle EOB must be equal to 180 degrees. The sum of those two angles must be equal to 180 degrees according to rule number 1. Here we subtract 90 degrees from this equation and we'll get that the missing angle, angle EOB, is equal to 180 degrees minus 90 degrees, it is 90 degrees. Okay, so the missing angle equals to 90 degrees. Well, we write it down, this angle equals to 90 degrees. So, if angle EOB, this angle equals to 90 degrees, it means that triangle EOB is a right triangle. The pink triangle EOB is a right triangle. Therefore, we can implement the Pythagoras theorem on this right triangle, triangle EOB. So I copy triangle EOB in a new page and we'll implement on it the Pythagoras theorem. So this is triangle EOB that I copied from the original drawing. We know that EO equals to the square root of 5 units, OB is the radius of the semicircle that is equal to the square root of 10 units, so, and the only thing that is missing is the hypotenuse AB. So we will use the Pythagoras theorem in order to find out the hypotenuse of the right triangle EOB. So here I write down by PT. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is EB here, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to ED squared plus OB squared. So EB squared equals to ED squared. ED equals to the square root of 5, therefore ED squared equals to the square root of 5 squared plus dB squared. dB equals to the square root of 10, therefore dB squared equals to the square root of 10 squared. In conclusion, we found out that EB squared equals to the square root of 5 squared, that is 5, plus the square root of 10 squared, that is 10. So in conclusion, we found out that EB squared equals to 5 plus 10, that is 15. We take a root out of this equation and we get that EB equals to the square root of 15 units. EB equals to the square root of 15 units. Okay, so we found out that the hypotenuse EB equals to the square root of 15 units. I write it down in the original drawing. Here EB equals to the square root of 15 units. Our mission is to find out the length of chord CB. The length of chord CB equals to CE plus EB. Okay, CB equals to CE plus EB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of chord CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we will make a construction. First of all, we will complete the semicircle to a circle. So in the first step, we completed the semicircle to a circle. In the next step, we will extend line segment EO on both sides. That is to say, we will extend line segment OE towards the upper side of the circle by a straight line, so until it touches the circle, and we will define the touching point of the extended side OE in the circle is point M. In the next step, we will extend line segment EO towards the lower side of the circle until it touches the circle, and we will define the touching point of the extended line segment EO in the circle is point N. Here, what is the length of line segment NO? Line segment NO starts from point O, that is the center of the circle, and ends at point N, that is the point on the circle itself. This is exactly the definition of a radius, that is to say, ON equals to the radius of the circle, that is equal to square root of 10 units. Why? Because the radius of the circle and the semicircle are the same. So, here, what is the length of EN? This is line segment EN. This is line segment EN. The length of EN, actually here, the length of EN equals to EO plus ON. EO plus ON equals to EN. I write it down. EN equals to EO plus ON. That is to say, EN equals to EO. EO equals to the square root of 5 plus ON. ON equals to the square root of 10. So in conclusion, we found out that EN is equal to the square root of 10 plus square root of 5. Okay, so EN, this line segment EN equals to the square root of 10 plus square root of 5. Okay. What is the length of line segment ME? The length of this line segment ME. From the drawing, it is very easy to see that ME equals to MO minus EO. I repeat again, ME equals to MO minus EO. MO minus EO equals to ME. Very simple, we can see it easily from the drawing. So ME equals to MO. MO is the radius of the semicircle. Why? Because it starts from the center of the semicircle, that is to say from point O, and ends at point M. Therefore, ME equals to, it is the radius of the semicircle, that is equal to the square root of 10 units minus EO. EO equals to the square root of 5 units. So in conclusion, we found out that ME equals to the square root of 10 units minus the square root of 5 units. So I write it down that ME equals to the square root of 10 minus square root of 5. In the next step, I present to you a new rule, rule number 2, and we will implement the new rule in our drawing. According to rule number 2, that is true in any circle, we can write down that in any circle, if chord AB, this is chord AB, again, this is chord AB, intersects with chord CD, this is chord CD, at point O. The intersection point between the two chords is happening at point O. So if it is the equation, then according to rule number 2, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, AO times OB equals to CO times OD. So we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN, this is chord MN that intersects with chord CB at point E. Again, chord MN intersects with chord CB at point E. So we copy the new chords with a circle in a new page and we implement on our drawing the rule number 2. We know that chord MN passes from the center of the circle, this is to say from point O. Chord MN intersects with chord CB, this is chord CB, at point O, at point E. Again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, so first of all, I'll write it down. So, our specific drawing chord MN intersects with chord CB at point E. This is the intersection point between the two chords. Therefore, according to rule number 2, we'll get that ME times EN Okay, so repeat again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times CB. ME equals to the square root of 10 1 square root of 5. EN equals to the square root of 10 plus square root of 5. And EB equals to the square root of 15. So here ME equals to the square root of 10 1 square root of 5. So we substitute ME by square root of 10 1 square root of 5. And EN equals to the square root of 10 the square root of 10 . again ME equals to the square root of 10 minus square root of 5, so we substitute ME by square root of 10 minus square root of 5. En equals to the square root of 10 plus square root of 5. And it is equal to CE, that is the missing 9 segments, so we leave it as it is, times EB. EB equals to the square root of 15, therefore we substitute EB by square root of 15. In conclusion, we found out that square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. Here we'll change the orders of two expressions, those two expressions, according to the algebraic rule that A times B equals to B times A. According to this rule, we can change the order of the two expressions. Therefore, okay. So we'll change the order of the two expressions. It will be square root of 10 plus square root of 5 times square root of 10 minus square root of 5. That is equal to CE times square root of 15. So we have here square root of 10 plus square root of 5 times square root of 10 minus square root of 5. We will solve this algebraic identity according to the. We will solve this. We will solve the. Find the value of this expression according to the algebraic identity that states that A plus B times A minus B equals to A square again A plus B times A minus B. The algebraic identity states that A plus B times A minus B equals to A square minus B square. According to this algebraic identity, A equals to the square root of 10 and B equals to the square root of 5, and A plus B times A minus B equals to A square minus B square. That is to say, this expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5 will be equal to A square minus B square. So what is A square minus B square in our specific expression? A equals to the square root of 10, therefore A square will be equal to square root of 10 squared, that is 10, minus B square. So B equals to the square root of 5, therefore A square will be equal to 5. So in conclusion, we found out that A square minus B square equals to 10 minus 5. Okay. And according to rule number 2, this expression, square root of 10 minus square root of 5 times square root of 10 plus square root of 5, that is A square minus B square, it is equal to CE times square root of 15. Okay, so in conclusion, we found out that our original expression, square root of 10 minus square root of 5 times square root of 10 plus square root of 5, that is equal to CE times square root of 15, it is equal to 10 minus 5, that is equal to CE times square root of 15. 10 minus 5 is 5, so 5 equals to CE times square root of 15. Okay, so we found out that 5 equals to CE times square root of 15. Here we divide this equation by square root of 15 and we find out that CE equals to 5 over square root of 15. Okay. Our mission is to find out the length of this chord called CB. But CB equals to CE plus EB again. CB equals to CE plus EB. I'll write it down. CB equals to CE plus EB. So CB equals to CE we just right now found out that CE equals to 5 over square root of 15. Okay, CB equals to 5 over square root of 15 plus EB. We've already found out that EB equals to square root of 15. So the answer to the question is that CB equals to 5 over square root of 15 plus square root of 15. This is actually CE plus CB. So that is the answer to the question. Here we simplify this expression. We don't want square root in the denominator, so we find out the common factor of those two expressions. In this way we eliminate the square root in the denominator. So we'll actually here CB it is equals to 5 over square root of 15 plus square root of 15. So we will multiply square root of 15 by square root of 15 and then we divide it by square root of 15. Square root of 15 over square root of 15 is 1. We actually multiplied square root of 15 by 1, so we change nothing. Therefore, it is allowable. So in conclusion, we found out that CB equals to 5 plus square root of 15 times square root of 15 is 15. So in the numerator we have 5 plus 15 over square root of 15. Okay, CB equals to 5 plus 15 over square root of 15. CB equals to 5 plus 15. 5 plus 15 is 20, so in the numerator we have 20 over square root of 15. Again, we don't want square root to the denominator. Therefore, we will multiply this expression by square root of 15, and then we will divide it by square root of 15. We actually multiply it by 1, so we change nothing. But in this way, we will eliminate the square root in the denominator. So we have CB equals to 20 over square root of 15. Here we will multiply this expression by square root of 15, and then we will divide it by square root of 15. So we found out that CB equals to 20 times square root of 15 over square root of 15 times square root of 15 is 15. Here we will divide both the numerator and the denominator of this expression by 5, and we get that CB equals to 20 over 5 is 4. So in total we have the denominator 4 times 15 over 15. Over 15, we actually divided both the numerator and the denominator by 5. So it is here in the denominator we have 15, therefore we have to divide it by 5. 15 over 5 is 3. In conclusion, we found out that here the length of this chord, the chord that we are looking for CB, it is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equal to 5.164 units. We finish with the question. In the next step, I will summarize the lecture. Okay. So, in the original drawing, we had the semicircle. We know that the center of this semicircle is at this point, point O. We also know that inside this semicircle we have this square, DEFO, and we know that the area of this square is equal to 5 square units, and our mission is to find out the length of this chord, chord CB. Okay. So, first of all, because of the fact that DEFO is a square, this is a square, we know that all the angles inside any square are equal to 90 degrees. They are all right angles. Therefore, those 4 angles, they are all right angles. And what is the area of any square? So if this is square ABCD, we know that all the sides of any square are equal to each other. So if we define one side of this square ABCD as x, then the other 3 sides will also equal to x, right? Because all the sides of any square are equal to each other. So what is the area of this square ABCD? That could be any square. The area of this square ABCD, it is equal to x times x. So x times x is x squared. So the area of this square ABCD is equal to x squared. In the next step, I copied the right triangle. I copied the square DEFO in this new page, and used the new formula in order to find out the length of one side of this square DEFO. So for one side, we know that the area, if we define this one side of this square DEFO as x, we know that the area of this square must be equal to x squared according to this formula. This is the area of square ABCD. That could be any square. Therefore, it could be also square DEFO, and the area of square DEFO, if one side is equal to x, it will be equal to x squared according to this formula. Okay, from one side, the area DEFO is equal to x squared. From the other side, it is given us the equation that the area of square DEFO is equal to 5 square units. Okay, so from those two expressions we can conclude that x squared equals to 5. Okay, here we took out all of this equation and found out that x equals to the square root of 5. So we know that all the sides of our square DFO all the four sides of this square DFO are equal to the square root of 5 units each of them. In the next step, we join points D and O together by straight line. By joining points D and O, we created the green light triangle DFO. So I copied the green light triangle here. We know that DF equals to the square root of 5 units, FO equals to the square root of 10 units, this angle equals to 90 degrees. The only thing that is left to find in a triangle, the right triangle DFO is the value of the hypotenuse DO. So by Pythagoras theorem, we know that according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is DO, therefore DO square is the square of the hypotenuse, and so according to the Pythagoras theorem, df square plus f whole square equals to d whole square. Okay, so d whole square, that is the square of the hypotenuse, equals to df square. Df equals to the square root of 5, therefore df square equals before that, df equals to the square root of 5, therefore df square equals to the square root of 5 square plus fo square. Fo equals to the square root of 5, therefore fo square equals to the square root of 5 square. So in conclusion, we found out that do square equals to the square root of 5 square plus square root of 5 square. So do square equals to the square root of 5 square, the square root of 5 square is 5, plus the square root of 5 square, it is 5. In conclusion, we found out that do square equals to 5 plus 5, that is square, that's 10. Then we took out of this equation we found out that do square equals to 10. We took out of this equation, we found out that do equals to the square root of 10 units. So here, DO, that is the hypotenuse of the right triangle DFO, it is equal to the square root of 10 units in its length. Okay. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. According to the new rule, this is actually rule number 1. The sum of the angles on one side of a straight line is equal to 180 degrees. So what is the meaning of this rule, rule number 1? Here we have the straight line AB, and we choose any point between points A and B. We choose point K, and we have here side KL. According to this rule, rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So we'll focus on one side, that is to say we'll focus on the upper side of the straight line AB, it's point K. Here the sum of the angles must be equal to 180 degrees. That is to say, the sum of those two angles, those are the two angles that we have at the upper side of AB at point K. The sum of those two angles must be equal to 180 degrees according to this rule number 1. So this is angle AKL and this angle is BKL. So in conclusion, angle AKL plus angle BKL, the sum of those two angles must be equal to 180 degrees according to this rule number 1. Okay, so we can implement rule number 1 in our drawing. Why? Because in our drawing we have we know that this is a semicircle. This part, it is almost the diameter of the semicircle. That is to say, AB is the diameter of the semicircle. So AB is the diameter of the semicircle. It's absolutely a straight line. Okay. Here, AB is the diameter of the semicircle. It is a straight line. So if we focus at the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees according to rule number 1. So here, at the upper side of the straight line AB at point O, the sum of the angles must be equal to 180 degrees. Which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle EON. In total, the sum of those two angles must be equal to plus angle, this angle is actually angle EOB. Okay, so 90 degrees plus the missing angle, that is angle EOB, this angle, in total must be equal to 180 degrees according to this rule number 1. Okay, so here you can see 90 degrees plus angle EOB must be equal to 180 degrees according to rule number 1. Here we subtracted 90 degrees from this equation and we found out that the missing angle EOB, this is the missing angle, this angle equals to 90 degrees. So because of the fact that angle EOB equals to 90 degrees, it means that this triangle EOB, the right triangle EOB is the pink triangle EOB is the right triangle. Therefore we can implement the Pythagoras theorem of this right pink triangle EOB. So I copy the right pink triangle in this page. This is the triangle. We know that EO equals to the square root of 5 units, OB equals to the square root of 10 units. This angle equals to 90 degrees according to rule number 1. And our mission is to find out the length of the hypotenuse EB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. So EB squared, that is the square of the hypotenuse, must be equal to EO squared, that is square root of EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared, plus OB squared. OB equals to the square root of 10, therefore OB squared must be equal to the square root of 10 squared. So in conclusion, we found out that EB squared equals to the square root of 5 squared plus square root of times plus square root of 10 squared. So EB squared, the square of the hypotenuse, must be equal to the square root of 5 squared. The square root of 5 squared is 5 plus the square root of 10 squared, that is 10. So EB squared equals to 5 plus 10, 5 plus 10 is 15. So we found out that EB squared equals to 15. Here we took a root out of this equation and found out that EB equals to the square root of 15 units. Okay, here EB equals to the square root of 15 units. And here also this is EB, that is equal to the square root of 15 units according to what we just right now found out. Okay, our mission is to find out the length of this chord called CB. We already found out that EB equals to the square root of 15, so the only thing that is left to find is to find out the length of CE. Why? Because CE plus EB is equal to the length of CB. Okay. In order to find out the length of line segment CE, this line segment, we did the construction, we completed this semicircle to a circle, then we extended OE on both sides. We extended OE towards the upper side of the circle, and this touches the circle at point M. We extended line segment EO towards the lower side of the circle, and it touches the circle at point N. What is ON? ON is the radius of the circle because of the fact that it starts from the center of the circle and ends at point N is the point of the circle itself. Therefore, ON is the radius of the circle that is equal to the square root of 10 units. And what is the length of EN? It is very easy to see that EN equals to EO plus ON. Again, EN equals to EO plus ON. EN equals to EO plus ON. That is to say, EN equals to EO. EO is the square root of 5 units plus ON, that is the square root of 10 units. So in conclusion, we found out that EN EN equals to the square root of 10 units plus square root of 5 units. Then we found out the length of this line segment ME. From the drawing, it is very easy to see that ME equals to MO minus OE. Again, ME equals to MO minus OE. Okay. So, ME equals to MO minus OE, and actually OM is the radius of the circle that is square root of 10 units minus OE that is square root of 5 units. So we already found out that ME equals to the square root of 10 units minus square root of 5 units. Okay. So ME equals to the square root of 10 units plus square root of 5 units. EN equals to the square root of 10 plus square root of 5, and finally EB equals to the square root of 15. Okay. Then I presented to you a new rule and implemented the new rule in our drawing. According to the new rule, that is actually rule number 2. Rule number 2 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, again, if chord AB intersects with chord CD at point O is the intersection point between the two chords, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So this is actually rule number 2, and we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is chord MN that passes through the center of the circle, that intersects with chord CB. This is chord CB. It's point E. Point E is the intersection point between the two chords. Okay. So copy the two, the circle and the two chords that intersect with each other. Again, chord MN. This is chord MN that intersects with chord CB. It's point E. Okay. Therefore, we can implement here rule number 2. According to rule number 2, ME times EN equals to MO times NC. Mm. So again, chord in our specific drawing, chord MN intersects with chord CB at point E. Again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. ME times EN equals to CE times EB. Okay, we have already found out that ME equals to the square root of 10 minus square root of 5, therefore we substitute ME by square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5, so we substitute EN by square root of 10 plus square root of 5. C is the missing line segment, so we left it as it is, and we have already found out that EB equals to the square root of 15, so we substituted EB by square root of 15. And we got that square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. In order to find out the value of this expression, but before that, here we use the algebraic identity that A times B equals to B times A. Therefore, we can actually substitute the two sides by each other. We will substitute the order of the two sides. That is to say, this will be the first expression and this will be the second expression. So, therefore, we actually got here square root of 10 plus square root of 5 times square root of 10 minus square root of 5 equals to CE, that is the missing line segment, times square root of 15. So in order to find out the value of the expression square root of 5 plus square root of 10 times square root of 5 minus square root of, again, in order to find out the value of the expression square root of 10 plus square root of 5 times square root of 10 minus square root of 5, we use the algebraic identity that states that A minus B times A plus B times A minus B equals to A squared minus B squared. Okay? In our specific expression, the value of A is equal to the square root of 10 units. A equals to the square root of 10 units and B equals to the square root of 5 units. And A plus B times A minus B equals to A squared minus B squared. That is to say, our expression square root of 5 plus square root of 10 plus square root of 5 times square root of 10 minus square root of 5 must be equal to A squared minus B squared. Why? Because A plus B times A minus B equals to A squared minus B squared. But what is A squared minus B squared in our specific expression? If A equals to the square root of 10, then A squared must be equal to 10. If B equals to the square root of 5, then B squared must be equal to 5. And A squared minus B squared equals to 10 minus 5. So our expression equals to 10 minus 5. Therefore, we can substitute our expression by 10 minus 5. And our expression equals to, according to rule number 2, it is equals to CE times square root of 15. Okay, it is equal to CE times square root of 15. And therefore, 10 minus 5 equals to CE times square root of 15. 10 minus 5 is 5, so we found out that 5 equals to CE times square root of 15. Here we divided this equation by square root of 15 and found out that CE equals to 5 over square root of 15. Okay? And we have to find out the value of chord CB. CB equals, again, CB equals to CE plus EB. Again, CB equals to CE plus EB. Okay, from the drawing it is very easy to see that CB equals to CE plus EB. We've already found out that CE equals to 5 over square root of 15 and EB equals to the square root of 15. So the answer to our question is that the length of this chord CB, the chord that we are looking for, equals to 5 over square root of 15 plus square root of 15. Okay, here we just simplified this expression because we don't want to have square root in the denominator. In order to eliminate the square root, that is minus square root of 15 in the denominator, we found the common factor of square root of 15 between the two expressions. In this way, we actually eliminated the square root of 15 in the denominator. Why? Because here CB equals to 5 over square root of 15, and then we took square root of 15 and we multiplied by square root of 15, and then we divided by square root of 15. Square root of 15 times square root of 15 is 1. It is allowable to multiply anything by 1 because you change nothing by it. Okay, so we did a correct operation that is allowable. So here CB equals to 5 over square root of 15 plus square root of 15 times square root of 15 over square root of 15. We multiply square root of 15 by 1, so we change nothing. So in conclusion, we found out that CB equals to 5 plus square root of 15 times square root of 15 is 15. So in the numerator we have 5 plus 15, in the denominator we have square root of 15. So CB equals to 5 plus 15 is 20, we have 20 in the numerator, and the denominator we have square root of 15. So in conclusion, we found out that the length of the line segment that we are looking for, or chord that we are looking for, CB, equals to 20 over square root of 15. But again, we don't want square root in the denominator, so we took this expression and then we multiplied by square root of 15, and then we divided by square root of 15. Again, square root of 15 over square root of 15 is 1. And it is allowable to multiply anything by 1 which has nothing. Therefore, it is allowable. Again, we multiplied this expression 20 over square root of 15 by square root of 15, and then we divided by square root of 15. And we got that CB equals to 20 times square root of 15 in the numerator, and in the denominator we have square root of 15 times square root of 15, that is 15. So we found out that CB equals to 20 times square root of 15 over 15. Here we divided both the numerator and the denominator of this expression by 5. Okay, so here 20 over 5 is 4. So in total we have in the numerator 4 times square root of 15. In the denominator we have 15, so we divided 15 by 5. 15 over 5 is 3. So in the denominator we have 3. In conclusion, we found out that the length of this 9 segment of chord CB, the chord that we are looking for, it is equals to either the length of this chord, it is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, the length of this chord CB equals to 5.164 units. Okay, thank you very much.